Lecture 5, Size of Vector Clock, Matrix Clock, Virtual Time and Physical Clock Synchronization. These are the topics of Lecture 5. Preface, recap of previous lecture. In previous lecture we have discussed the models of distributed computation and presented the idea of causality and logical time that was proposed by Lampert in 1978 in an attempt to order the events in a distributed systems. We have discussed two systems of logical clock, namely scalar and vector clocks, to capture causality between events in a distributed system. Content of this lecture. In this lecture we will discuss about the size of vector clocks, matrix clock, virtual time and physical clock synchronization. So in the last class we have seen the concept of causality, which is a fundamental in the design of distributed systems. Usually causality is tracked using physical time. Now physical time in day-to-day life we also use it in the form of the loosely synchronized clocks which we have in the form of wristwatch, wall clocks and so on. Our activities are timed using access to these clocks. In computer, in centralized system, that is, in a centralized system there is a single clock, and the processes using the issue of the system calls, they can access the computer clock, and the events or the processes can get the time out of it. The next process, when demands a time, it will get the next time and so on. So in a centralized system there is no need of clock synchronization. In a distributed system, processors have their clocks loosely synchronized, all the clocks, and as far as synchronization of a clock is concerned becomes a big problem, and we are going to see in this particular topic today all these aspects of causality, how we are going to obtain the causality in a distributed system, and physical clocks or a logical clock, whichever of them is going to be useful for a design of distributed system. So in the last class we have seen the logical clocks in two forms. The first is called scalar clock, the other was the vector clock. Scalar clock provided the clock consistency property, and the vector clock provided the strong consistency property. So the applications which needs them will be basically going to use them. Today we are going to see that the size of the vector clocks, why it is required to be the size of the number of processes, that is called n. So that is called size of vector clock. Is it required to have n always, or we can basically work with less than n, still we can have the strong consistency property. Let us go ahead. So size of vector clocks, an important question to ask is whether the vector clocks of size n are necessary in the computation consisting of n processes. To answer this question we have to examine the usage of vector clocks. So usage of a vector clock means the applications where we are going to use them will answer this kind of question. So the vector clock provides the latest known local time at each other process. So if this information in the clock is to be used to explicitly track the progress at every other process, then vector clock of size n is necessary. Now a popular use of vector clock is to determine the causality between the pair of events. Given any events E and F, the test that E has happened before F if and only if the time stamp of E is smaller than time stamp of F, which requires a comparison of vector clocks of E and F. Although it appears that the size of n is necessary, that is not quite accurate, that we are going to see here. It can be shown that the size equal to the dimension of a partial order, that is E and that happened before relation, is necessary. where the upper bound on this dimension is n, not the size of n. So the definitions in this regard we are going to see. To understand this result on the size of clocks determining the causality between the pair of events, we first introduce some definitions. Linear extension of a partial order is the linear ordering of E that is consistent with the partial order. That is, if two events are ordered in a partial order, they are also ordered in the linear order. So linear extension can be viewed as projecting all the events from different processes on a single time axis. The dimension of a partial order is the minimum number of linear extensions whose intersection gives exactly the partial order. So having given this particular definition of a linear order, so now we are going to see that linear order will necessarily introduce the ordering between the pair of events, and some of these orderings are not in a partial order. Also observe that different linear extensions are possible in general, and let capital P denote the set of tuples in a partial order defined by causality relation. So there is a tuple EF in P for each pair of events EAF such that E has happened before F. Let linear extensions L1, L2 and so on denote the set of tuples in different linear extensions of this partial order. The set capital P is contained in the set obtained by taking the intersections of such collections of linear extensions L1, L2 and so on. This is because Li contains all the tuples, that is the causality dependencies that are in P. Now let us take one example when there is a client server interaction application. Now here the client server interaction happens between a pair of processes. The queries to the server and the responses to the client occur in a strict alternating sequences. Although n is equal to 2, that is client and server, all the events are strictly ordered and there is only one linear extension of all events that is consistent with the partial order. Hence the dimension of this partial order is 1. So the scalar clock, such as one implemented by the Lampert's scalar clock rules, is adequate to determine E has happened before F for any two events. So here only, although n is equal to 2, but only the size of the clock is 1 required to solve this application. Similarly, another application which is called concurrent send and receive. So now consider an execution on processes P1 and P2 such that each send a message to the other before receiving the other's message. So the two send events are concurrent, as are the two receive events. To determine the causality between the send events or between the receive events, it is not sufficient to use a single integer. A vector clock of size 2 is necessary. This execution exhibits a graphical property called crown. So a crown of n messages has n dimension. So we are going to see another example of a complex execution. So in a complex execution, to determine the dimension of a partial order is not going to be straightforward. Next figure 5.1 shows an execution of 4 processes. However, the dimension of this partial order is going to be 2. So that is a vector clock of size 2 is good enough to provide the strong consistency property among the 4 process interaction in this particular example. To see this informally, let us consider the longest chain A, B, D, G, H, I, J. There are events outside this chain that can yield multiple linear extensions, hence the dimension is more than 1. The right side of figure 5.1, we are going to show now that earliest possible and the latest possible occurrences of the events are not in this chain with respect to the events in this particular chain. See this particular example here. So in this example, we have seen so the longest linear extension chain, that is A, B, D, then G, H, I and J. So that is mentioned over here, the longest. Now out of this particular longest chain, what we can see here, these are basically the events which are outside this particular chain, that is C, E and F. So C, E and F, basically outside the chain. So now we are going to form the linear extension. So two linear extensions are possible here in this case. So obviously the dimension of the partial order is not going to be 1 but more than 1. So two linear extensions, if we see, is possible with the earliest time and the latest time of C, E and F. So there are two different linear extensions are possible who are here in this case, and these two linear extensions, if we take intersection, it will give the partial order set. That is what is going to be shown here in this particular complete illustrative example. So L1 is a linear extension, L2 is another linear extension, and when L1 minus partial order set P intersection L2, it becomes empty or a phi. Similarly, L2 is a linear extension minus P intersection L1 is also giving the empty one. So hence the intersection of L1 and L2, these are the two linear extensions. This will basically generate the complete partial order. Hence the dimension of this particular execution is 2. So that means two linear extensions are good enough to generate this partial order. Hence the vector clock of size 2 is good enough to ensure the strong consistency property, and hence basically to solve this application. So all for the total number of processes is equal to 4. So only the vector clock of size 2 is required here in this particular case. So finding out the dimension of the partial order is not going to be easy. Computationally is going to be difficult. So basically posterior analysis is required here in this case to identify the size of the vector clock, and it can be optimized, and different algorithms are going to use this kind of concept in reducing the size of the vector clock. Now the next clock we are going to see is called the matrix time or a matrix clock. So in a system of matrix clocks, the time is represented by a set of n by n matrix of non-negative integers. So let us go and see the details of the matrix time. A process Pi maintains a matrix MTI n by n, where MTI I comma I denotes the local logical clock of Pi and tracks the progress of computation. So it is going to be working like a scalar time, like we have seen in the scalar clock. The other component, that is called MTI I comma j, denotes the latest knowledge of process Pi has about local logical clock of process Pj. So that means this particular aspect will give you something called vector time. The notion of a vector time is given here in this case. Now the third aspect of a matrix time, that is MTI j comma k, represents the knowledge that Pi has about the latest knowledge that Pj process has about the local logical clock of Pk. This global information is stored in the local view of process Pi. So the entire matrix Pi denotes the Pi's local view of the global logical time here in this matrix clock. Now the two rules which matrix clock used to follow to update its clock is R1 and R2. We are going to explain it. So the rule R1, before executing an event, process Pi updates its local logical time as follows. So it will be done according to the scalar clock that we have already seen. The rule R2, each message M is piggybacked with a matrix time MT. When Pi receives such a message containing that particular matrix timestamp message from Pj, then Pi executes the following sequence of actions. So it will update its global logical time as follows. So that means MTI, that is PI process, for its ith row, that is ith vector, it will update as per the information, as per the time, which is as per the matrix which is received by that particular process Pj. So it will be like updating the vector clock. Now the remaining portion of the matrix of I will be updated like this. So basically for k which is greater than 1, that means for all other rows, and also the complete vector of the basically the rows of other processes are going to be updated as per the information which is being obtained from the message which has basically sent its the matrix timestamp. After doing this updation according to the rule R2, it will execute R1 and it will deliver the message M. So example 1, you can clearly see that event E1 is represented here in the matrix, and this particular element is representing the local clock or the scalar time of process 1. Now this particular matrix, when it sends a message according to the event 1, which is message send event, similarly event 3 also will basically have this kind of matrix, because the third row and the third column will basically indicate the scalar time of process P3. Similarly, when they will be received at E2 of a process P2, so now let us see the details how it will be basically updating the clock. So process P2, first it will basically modify its scalar clock, so that is in the second row and the second column, so it will be the event number 1. Now as far as the time which it has received, that will be updated based on the information, based on the local view of the other process. For example, process 1 has its clock 1, so it will be updated over here. Similarly, process 3 has a clock value 1, so it will be updated. So this will be the vector clock kind of updation which we have seen. The remaining part, this portion will be copied here, and the last portion also will be copied here. So the P2 will have the view of the P3's time. Similarly, the P2 will have the view of P1's time, and this particular updation is done according to the matrix clock rule which we have seen. In another example, you can see when this particular message is received to P2, so P2 means its vector at the second row. Now its particular event, that is the scalar event, is first updated, and then it will update the vector time. So vector time means the time of 1 will be updated over here, and 0 means it has not seen about any event from P3, and this will be copied over here as far as the third updation, that is the matrix clock, which is the copying the vector of other processes which P2 will have the knowledge. Similarly, about the other interactions you can see. Finally, you can see that the event E3, which has complete view of all the events which has happened. So let us see its vector now. So E3 means, so it is about the process P3. Now its event that is at the second event, because E32, if you see it is second event, so that means its scalar time is 2 and its vector will be 2 comma 3. That means it has seen so far the message which is coming from 2. So 2 means it is having 3, so it will be updated over here. Similarly, it is having the vector 2, so it will be updated. So the vector clock and scalar clock both are updated. Now as far as the vectors of other processes are concerned, so it will be copied. Similarly this also will be copied over here. So this is the matrix time, and we have seen the working of a matrix clock. What are the basic properties of a matrix clock that we are going to see now? So the vector MTI, that is the ith row, that is nothing but the complete vector. It will have all the properties of a vector clock. In addition, the matrix clock have the following properties. That means all the processes which is having the minimum value of k, which has seen which is basically having the information at the pith. So minimum value is basically t. So that means process pi knows that every other process, that is process pk, knows about pi's local time has progressed until t. Having this information, there are many applications which will require this information, which says that the other processes will no longer require the information from pi, which is basically before the time t. Hence they can discard this obsolete information in this particular manner. Now the next time system we are going to consider is called virtual time. Now virtual time system is a paradigm for organizing and synchronizing distributed system. So this particular section we are describing the virtual time and its implementation using time wrap mechanism. The implementation of a virtual time using time wrap mechanism works on the basis of optimistic assumption. What is that optimistic assumption? Time wrap relies on a general look-ahead rollback mechanism where each process executes without regard to the other processes having synchronization conflict. If a conflict is discovered in the optimistic assumption, the offending process are rolled back to the time just before the conflict and executed forward along the revised path. Detection of conflicts and rollback are transparent to the user. The implementation of virtual time using time wrap mechanism makes the following optimistic assumption: that synchronization conflict and rollbacks generally are occurred rarely. So it's not a frequent operation for the rollback or a conflict. So virtual time is a global one-dimensional temporal coordinates on a distributed computation to measure the computational progress and to define the synchronization. A virtual time system is a distributed system executing the coordination with imaginary virtual clock that uses virtual time. So virtual times are real values that are totally ordered by the operation, by the relation called less than relation. So virtual time is implemented a collection of several loosely synchronized local virtual clocks. These local virtual clocks move forward to a higher virtual times. However, occasionally they may move backwards whenever there are conflicts. So virtual time processes can concurrently communicate with each other by exchanging message. So every message is characterized by 4 values in virtual time. Name of the sender is there, virtual send time is there, name of receiver and virtual receive time is there. Now virtual send time is the virtual time of the sender when the message is sent, whereas virtual receive time specifies the virtual time when the message must be received by the receiver. So the problem arises when the message arrives at a process late. That is, the virtual receive time of the message is less than the local virtual time at the receiver process when the message arrives. So this is going to be handled here in virtual time. So virtual time systems are subject to two semantic rules similar to the Lampert's clock conditions. Rule 1 says that virtual send time each message has should be less than the virtual receive time of that particular message. Otherwise there will be a problem, and problem will be resolved using the rollback. Rule 2 says that virtual time of each event in the process is less than the virtual time of the next event in that particular process. This is going to be solved using the global clock system. So the above two rules imply that the process sends all the message in the increasing order of virtual send time, and the process receives all the message in the increasing order of the virtual receive time. Now it is important, an event that causes another should be completely executed before the caused event can be processed. This is already indicated in rule 1 and rule 2. So we are now going to see the characteristics of a virtual time. Virtual time systems are not all isomorphic. It may be either discrete or continuous. Virtual time may be only partially ordered. Virtual time may be related to the real time or may be independent of it. Virtual time system may be visible to the programmers and manipulated explicitly as the values are hidden and manipulated explicitly according to some system defined discipline. Virtual times associated with the events may be explicitly calculated by the user program or may be assigned by fixed rules. So now we are going to see the comparison with Lampert's logical clock, how the virtual time is basically the different. So in the Lampert's logical clock, an artificial clock is created, one for each process with the unique labels from totally ordered set in a manner consistent with the partial order that we have seen. In virtual time, the reverse of the above is done by assuming that every event is labeled with a clock value from a totally ordered virtual time scale satisfying the Lampert's condition. Thus, the time warp mechanism is an inverse of Lampert's scheme. In Lampert's scheme, all the clocks are conservatively maintained so that they never violate causality. The process advances its clock as soon as it learns a new causal dependency. In the virtual time, clocks are optimistically advanced and corrective actions are taken whenever violations are detected. So time warp mechanism. So in the implementation of virtual time using time warp mechanism, virtual receive time of a message is considered as a timestamp. The necessary and sufficient condition for correct implementation of virtual time are that each process must handle incoming message in the timestamp order. Now the time warp mechanism consists of two major parts. The first is called local control mechanism. The second part is called global control mechanism. Local control mechanism ensures that the events are executed and the messages are processed in the correct order. The global control mechanism takes care of global issues such as global progress, termination, detection, I/O handling, flow control, etc. that we have seen in rule 1 and rule 2, and they are implemented in a time wrap mechanism. Now the next part of discussion, we are going to see that if different processors are having their physical clocks are going to be used in the distributed system, then how are we going to synchronize them? And for that we are going to see a protocol which is called a network time protocol, which does the physical clock synchronization. So let us begin this kind of discussion. In centralized system, there is only one single clock. The process gets the time by simply using the system call to the kernel. So the next process, if it gets the time, it will get always the higher time because it is getting from the same clock. So there is no problem of clock synchronization in centralized system. However, in a distributed system, there is no global clock or a common memory. Each processor has its own internal clock and its own notion of a time. These clocks can easily drift seconds per day, accumulating a significant error over the time. Also, because different clocks tick at different rates, they may not remain always synchronized, although they might be synchronized when they start. This clearly poses serious problem to the application that depends upon the synchronized notion of time. So the most practical application algorithm that run in a distributed system, we need to know the time in one or more of the following context. Now, unless the clocks in each machine have a common notion of time, time-based queries cannot be answered. So clock synchronization has a significant effect on many problems like secure system, fault diagnosis, recovery, and so on. So clock synchronization is the process of ensuring that physically distributed processors have common notion of time. Due to different clock rates, the clocks at various sites may diverge with time, and periodically clock synchronization must be performed to correct this particular clock skew in distributed system. In our day-to-day life, our wristwatch or our wall clock also loses the synchronization, and we do the synchronization with a universal coordinated time, that is UTC. So clocks are synchronized to an accurate real-time standard like universal coordinated time. They are not only going to be synchronized, but they have to be synchronized with a global clock or a physical time, and that is done through UTC, universal coordinated time. So clocks that must not be synchronized with each other but also have to adhere to the physical time are termed as physical clock. So physical clock means not only the synchronized set of clocks, but also they have to be coordinated or synchronized with the physical time, so they should be giving the same set of physical time. Now we are going to see into more detail of the clock synchronization, and finally we are going to basically see how these concepts are going to be used in network time protocol. So clock inaccuracies. Physical clocks are synchronized to an accurate real-time standard like universal coordinated time. It is also called UTC. However, due to the clock inaccuracies discussed above, a timer clock is said to be working within a specification where constant rho is maximum skew rate specified by the manufacturer. So that means the clock rate must be bounded by 1 plus rho and lower bounded by 1 minus rho. So if it is working in this particular equation, that is equation number 1, then we have to see that clock is working within the specifications. Otherwise, we can see in these situations, if that particular clock rate, that is dc by dt, is equal to 1, then it is perfect clock. If it is slow, then dc by dt is less than 1, and a fast clock dc by dt is greater than 1. So the behavior of fast, slow, and perfect clock are shown here in this particular diagram of a clock inconsistency. Offset delay estimation methods are used in a network time protocol. We are going to see what these methods are. So the network time protocol, which is widely used for clock synchronization on the internet, uses offset delay estimation method. The design of network time protocol involves hierarchy, that is hierarchical tree of time servers. So that means universal coordinated time will be synchronized in the form of a hierarchical tree. That is, the primary server at the root synchronizes with the UTC. The next level contains the secondary servers, which acts as a backup to the primary. At the lowest level is the synchronization subset, which has the clients. Clock offset and delay estimation. In practice, source node cannot accurately estimate the local time on the target node due to the varying messages or the network delays between the nodes. So this protocol implies a common practice of performing several trials and choose the trial with the minimum delay. Figure 5.4, we are going to show you the network time protocol timestamps, which are numbered and exchanged between the pairs A and B. Let T1, T2 and up to T4 be the values of 4 most recent timestamps as shown in the next figure. Assume clock A and B are stable and running at the same speed. So these are the 4 time we have now shown, and we are going to use it for offset and delay estimation. Now A is equal to T1 minus T3. So this particular portion will become A, that is T1 minus T3, and here this portion will become B, that is T2 minus T4, and this is going to calculate the offset and delay. So the clock offset, which is shown as a theta, is nothing but a plus b by 2, and the round trip delay, that is little delta, is nothing but a minus b. So each network time protocol message includes the latest three timestamps, that is T1, T2 and T3, while T4 is determined upon arrival. Thus both peers A and B can independently calculate delay and offset using a single bidirectional message stream shown here in this figure 5.5. Now with this particular figure 5.5 network time protocol, that is called time synchronization protocol, we are going to see. So a pair of servers in a symmetric mode exchange the pair of the timing messages. Store of data is then built up about the relationship between the two servers. Specifically, assume that each pair maintains a pair, that is OI and DI, offset and the delay. So OI is a measure of theta, that is the offset, and DI is the transmission delay of the two messages, that is little delta. The offset corresponding to the minimum delay is chosen, and that will be basically the OI. Minimum delay is basically the DI. So specifically the delay and offset are calculated as follows. Assume that the message M takes time t and message M prime takes t prime to transfer the message. So now the offset between A and B, A's clock and B's clock is, let us say, O. So A's local clock time is AT and B's local clock time is BT. We have AT is equal to BT plus O. Then another equation, question number 4, says that Ti minus 2 is equal to Ti minus 3 plus T plus O, with reference to this particular figure we are going to estimate. So same thing which we have seen in the previous slides, that is being calculated. Now assuming T is equal to T prime and offset OI can be estimated as OI is equal to Ti minus 2 minus Ti minus 3 plus Ti minus 1 minus Ti divided by 2. Similarly, round trip Di is estimated as Ti minus 3 minus Ti minus 1 and Ti minus 2. Now having calculated the equation number 6 and 7, so the 8 most recent, these pairs are retained. Retained means they are basically estimated, calculated. So the value of OI that corresponds to the minimum DI is chosen in the estimate of O. So that we have already seen. Now the question arises, we have seen the physical clock synchronization, we have seen several logical clocks. Now the question is whether the physical clock or a logical clock is used to capture the causality in distributed system. Which of these methods is good in a distributed system? Now in a day-to-day life, the global time, that is physical time, to deduce the causality relation is obtained from a loosely synchronized clocks like wristwatch and wall clocks. However, in distributed computing system, the rate of occurrence of the events is several magnitude higher and the event's execution is several magnitude smaller. So consequently, if the physical clocks are not precisely synchronized, the causality relation between the events may not be accurately captured. So this is the most important notion. Therefore, it turns out that in distributed computation, the causality relation between the events produced by the program execution and its fundamental monotonicity property can be accurately captured by the logical clocks. So if the physical clocks are used, and physical clocks using network time protocol, basically they can synchronize up to tens of milliseconds. But if the number of events which are several magnitude higher and the event execution time is several magnitude smaller, basically is not basically fit in to that accuracies, then physical clocks, even the network time protocol will not be useful for the distributed system applications. So we have to see what kind of application we are going to run, whether the physical clock can be used with a network time protocol, whether can it solve the problem or not. But definitely in all cases the logical clocks, which basically captures the fundamental monotonicity property, can be captured and can be useful in a distributed system. So obviously the logical clock in all situations, it will work perfectly fine for distributed application, and that is why we have seen so much of different kind of the logical clocks in this particular part of the discussion. So in conclusion, in this lecture we have discussed about the size of vector clock, the matrix clock, and the virtual time to capture the causality between the events in a distributed system. Then we have seen how the physical clock synchronization can be used as a paradigm for organizing and synchronizing the distributed system. In upcoming lecture, we will discuss about global state and snapshot recording algorithms.